in this 3 sessions that we have today, the idea is to give you a lot of information, but in a very structured way. And the objective is that with the tools that you will get today, you will be able to program, train a neural network by yourself, and be able to explore further architecture of neural network for your own purpose, for your own research. We will start from the very beginning. So we'll start from the real basics, meaning that we'll not just explain the main concept behind deep learning and machine learning in general, but we will be able to create them by ourselves using very basic tools of Python, of programming. First of all, how many of you have experience in programming? And how many of you have experience in programming with Python? Good. And how many of you have been working to some deep learning related application with Python? Okay. So most of you already have some experience. So we can, that helps us because it means that we can go quite fast over this first part and get to the more advanced application that we will see in the afternoon. But still, since some of you have never been playing around, messing around, let's say, with a deep learning architecture with Python, we will start from the very beginning. We will follow the structure of this book. You see here. I don't know if you already have it or you've been suggested to buy it, but I mean, in principle, our class will be structured around this, and we will go through the first 3 chapters. You will see that in these chapters there is a lot of code, and this code is also available online. So if you go to GitHub, and then you go to the organization that is called Deep Track AI, there you have a repository that is called Deep Learning Crash Course, which is the title of the book. And in this repo, you can find folders that are associated to each chapter of the book. And in each folder, for example, this is the first one that we will go through today. You can see that there are subfolders related to the different examples and to the different applications that we will see in the book. And for example, if we open the first one, you will have data to replicate the experiments, and also notebooks that we will use to show the examples, and a helper function that we will use, for example, to load the data or to plot them. Just to give you a flavor. So basically, this is a typical notebook, and the first one that we will go through today. And you see that we can, I mean, typically when we teach these classes, we ask the students to bring the computer and to run the code simultaneously as we do. But the typical way we teach it is that, I mean, the first 3 chapters that we will go through today are basically taught in 3 days. And today we will basically be compressing everything in 6 hours. So probably there won't be time to run all the examples by yourself on the laptop. But I mean, here you have all the code, and with the help of the instruction that you will get today, and with the book, you will be able to do that anyway. So let's start from very first concept. The field of deep learning and in general of machine learning and artificial intelligence started developing several decades ago. And one of the first objectives, let me see if I can make this bigger. Apparently not. Very difficult to scroll it down and make it bigger. Anyway, I mean, we will have to live with this. So one of the main idea was to be able to use a computer, a machine, to create the way the human brain works. And of course, the idea was to achieve that using mathematical operation implemented on a computer. So the basic unit for aiming to that objective was to build a neuron. But what is a neuron from the biological point of view? Is any of you familiar with the concept of neuron in biology? What's a neuron? A cell. Okay, it's a cell. What's the main function of this cell? To transmit information. Which form of information is this cell transmitting? An electrical pulse. So basically, I mean, if you see these schematics here, you have these cells that it's very branched, that's connected to other cells, and it's receiving information through the synapses. So basically, it's getting signals in, and it's signaling out. And the signaling out is what is called the firing. Huh? But the firing does not happen in all the situations. It depends on the signals in. So you get several signals pretty much simultaneously. This signal needs to be integrated. And depending on the result of the integration, the read neuron decides if firing or not. So if transmitting this information or not. So basically you have first concept, input, integration of this input, and then thresholding this input, deciding if you, based on the combination of the input, the neurons fire or not. From the mathematical point of view and from the, that it's relatively simple to implement, because basically what you have a vector of inputs that can be numbers, for example. And these inputs need to be integrated. And depending on the inside of the cell and cellular machinery, each input can have a different weight, can count more or less in the final integration that the cell does. So those can be mathematically described as weights. So other numbers that we have in here that are part of the neuron. The integration of these signals is just a linear operation. You multiply each input by its weight, and then you sum up together all these products. It's a linear combination of inputs. At this point, you have a number, so you have a quantity inside the neuron. And based on this quantity, the neuron must decide if firing or not, if sending signal to another cell or not. And at this point, we have to introduce something that is crucial. Because so far, what we have seen is linear operations. No? Basically, we have multiplication and sum. But the thresholding is nonlinear. You're introducing something that helps the neuron to make a decision if the output is, for example, going to be high or low, true or false, 0 or 1. So doing something that which output is binary. And this is achieved mathematically through an activation function. Activation function from the, very basic point of view can be just a step function. That, if the value, the integrated value, the activation potential is below a given threshold, the neuron does not fire. The signal output is 0. It's false. It's low, electrically speaking. If the number is above this threshold, then the neuron fires, and you have signaling. This can be implemented from the mathematical point of view, and we can see that, for example, using just NumPy. We need to find out a way to zoom up this a bit more, because otherwise it's going to be the 3 dots in, where are they?
I think usually you can do this.
No, it
No, it doesn't work.
Oh, maybe
it does.
Yeah, too much.
Something like that.
Yeah, that helps. But that is very.
It's too much.
No, it's that you cannot scroll continuously. You see? So you cannot really center it.
Maybe if you use the arrow keys.
Yes.
Works.
Yeah. Okay. So basically, what we need to do in order to implement this neuron is what we see here. We can put it in a fancy way, like defining a function in Python, And then we define this function neuron class 1D, and we will see later on why we call it this way. So basically what we do is that given two inputs that are the weights and a value of the input x, this function, we calculate the product, and then we do the logical operation of seeing this output is larger than 0 or not. In this case, we're doing something very simple. We're just comparing it with 0. And the output of the neuron is going to be this 1 or 0 output, depending on this number. But let's see this in action. And for applying this function, we need to use some data. And we will start with a very simple data set that it's that you can find it in the GitHub repo that I showed you before. And when playing with a data set, the first thing that it's very wise to do is just to see how the data look like. No? And basically, if we just load and print this data, we see that what we have is just an input vector that is made by these numbers. And then we have y underscore gt that is something associated to each input. Basically, we have the same number of elements in the x and in ygt. What does x represent? In the example that we want to show, basically, what we want to do, we want to use the neuron to learn a specific output based on the input. And in order to do that, we will use an approach that is called supervised learning, meaning that we force the network, the neuron, to learn on data of which we already know which is the output. So basically, if our operation is given the input, tell me if the neuron will fire or not, tell me if the output will be 0 or 1, we need to prepare a data set in which we already know if given that value, the output will be 0 or 1. And this is the data that we have here. So basically, we have prepared this data. This is based on a random simulation. And based on the input, we associate to each value of x a value of y. And we use the underscore gt to mean that those are the ground truth. So we already know what is the expected output given these inputs. We can plot this data. I mean, besides taking a look at them, we can just see how they look like in a scatter plot. And we see that they look like this. So basically, we have that small value, negative values of x correspond to y ground truth of 0. And then at some point, there's a change point. For some value on, this data start to give positive values. But this is just a prepared data set. I mean, we haven't done anything yet with our neuron. Now we want to use the neuron to try to understand how this data work. What is the relationship that generates this behavior in the data? What is the relationship that, given the x, produces this y? And basically, since the output is binary, what we want to do is a classification. I mean, in this very simple way, what we want to do, we want to classify numbers if they are positive or negative, which is something extremely trivial to do. But it's irrelevant to understand how this process works. So we have the data set. We have the neuron because we already built the, I don't know. We already built the function that we show here. Now we can try, for example, to apply this function to the dataset and see what is the output. But we miss one piece of information. What do we miss at the moment? We have the input. We have the expected output because the data already tell us that. We want to apply the neuron to the input data to see what the neuron predicts about this data. What are we missing? The function is here because basically, but the function depends on two inputs. No? One are the weights, and we don't have the weights. So the neuron calculates the given output based on some weights. So the approximation of the function given by the neuron depends on the weights themselves. And so far, we don't know what are these weights. But I mean, just to see how this function works, we can do something easy. What we do is to take some random weights. we generate a set of random numbers that corresponds to the weight. In this case, we've seen that basically we have inputs that is a vector. Well, our input vector is made of one input at a time. So basically, this is a very simple case in which the neuron gets one input and provides one output. It's basically classifying the number if it's positive or negative. So basically, in this case, we need one weight. And we can generate that randomly. For example, using the random library from NumPy. And then at that point, we have a W0, which is a random number that we can use as an input for our function, the function that describes the neuron that has two inputs. One is the weight, and the other one is the input number. And for example, this is what we do here. No? If we look at this line, we have YP, so it's the prediction of the neuron for given input X based on the weight W0 that we randomly produce is going to be stored in this vector in YP. And if we plot it, let me see if I can show just what do we see? So the black dots are the numbers, our simulations, not the data that we already had. And basically have the same behavior that we saw before. I mean, they have Y value equal to 0 when X0 is negative, then at some point it becomes positive, which is not exactly at 0, but I mean, it's close to 0. But then our prediction, so our application of the neuron with a random weight on the same input data produce results that it's quite different. What is going on here? The neuron is not able to approximate this function because basically we're just creating a random number. We're just saying, look, take a random number for the weight W0, multiply this value for the input X, and see if they are positive or negative, roughly speaking. Of course, you have two possibilities, that you get exactly the same behavior as before, as the input data, or the opposite behavior, because basically it's a binary classification. And in this case, in this run of the random generation, you get the opposite one. But I mean, the neuron so far hasn't learned anything, because basically the number, the weight that we are putting in is just a random number. We have to find a way to have the neuron understand or learn by itself which weight needs to be used to approximate the ground truth, to approximate the blue dots. So basically, we need an algorithm for that. We need a pipeline. And which pipeline can we think of? Okay, the pipeline that I will describe now is not exactly what is used nowadays in the for the learning of the deep learning architecture. It's something much basics, and the purpose of that is just to understand how the mechanisms work. It's not the most efficient way, let's say, but it helps to understand the learning process. Then we will see how the modern architecture and the learning process work in reality later on. But I mean, let's start from the very beginning. So imagine that we take one of the input at a time, randomly. So for example, we get the value of X0 here. And then we start with a random weight. For example, the same random weight that we have produced so far randomly. So we initialize the neuron in a random fashion. We calculate W0 times X0. We see if this number is positive or negative, and we compare it with the ground truth. The ground truth that is, in this case, 0. So let's suppose that with the first random generation, we get that the prediction of the neuron for this X0 value is 1. It's far off from the real value. So we need to use the difference between the prediction and the ground truth to correct the way. And what's the way to do that? Basically, one way is to, very simple, calculate the distance between these two. If the distance is large, I need to change the weight a lot. If the distance between the prediction and the ground truth is small, I have to change it a little bit. And if it's exactly the same, see if my prediction is already good, I do nothing. Then I correct the weight in this way. We have according to this rule. And then I take another random number, another of the X0 numbers that I generated before, and I do the same process. And then I iterate until I get that the prediction is good enough compared with the ground truth. So I have some way to stop my iterations when I see that, I mean, there's no further improvement, even though if I repeat this process over and over. So basically, the steps of this algorithm are summarized in here. I initialize the weights randomly, for example. I choose a random point, one of the data set that I have. I use this random point to calculate the prediction of the neuron on that point with a random weight. And I compare it with I compare the prediction with the ground truth. I calculate some sort of distance, and based on this distance, I correct the weight. I mean, here you can see the formula that we use. No, basically you have the difference between ground truth and prediction multiplied by the value of the input x, and then there is another parameter that is called eta. And this is what in deep learning is generally referred to as learning rate, which is one of the hyperparameters that you need to tune in order to have an efficient network, an efficient machine. What does it do? Basically, eta is something between 0 and 1. And basically tells you how far, I mean, given the difference between prediction and ground truth, how far you need to move in one direction or the other to approximate the best solution of the problem, to optimize the problem. It is crucial for two reasons, because basically, imagine that what we're doing is to find the minimum of a parabolic function, no? And then you get a prediction that is not exactly the minimum. So your prediction basically, so the distance of your prediction by the ground truth, it's one point in the x-axis of this, where this parabola is plot. Basically, what we're trying to optimize is the gradient of this parabola. What we're trying to optimize is to find the minimum based on the gradient of this parabola. Basically, if you're in a point that is far away from the minimum, you have a big gradient, which in this case will correspond to this difference, no? Roughly. Then it means that if this value is big, the gradient is big, you have to move a lot. But how much you have to move does not depend only on this difference. It also depends on the parameter eta. Now, if eta is very large, and you are in a point that it's far away from your minimum, you can start going back and forth from one side of the other of this parabolic function and never get to the real minimum. On the other side, if this eta is very small, you can be for a long time very close to your initial point and never get to the minimum. That's why this parameter needs to be tuned. And the tuning is based on some expertise, on knowledge of the problem you're dealing with, and on trial and error. I mean, there's no general rule. One thing that can be smart to do in many cases, and probably we'll see it in one of the examples of this afternoon, is to tune this parameter along the training. So start with something that is relatively large and then progressively reduce it. Because basically you assume that, at the beginning you have to move a lot to, or at least you have to move quite farther away from the initial point where you are to find the minimum. But then when you start getting in the neighborhood where the minimum is, you want to approximate it in the best possible way. So you move let's say, less at that point. But let's go back to our algorithm. I mean, just to make sure. Jesus, Henrik, feel free to jump in at any point to add up stuff or to correct me over that. So basically, once you have updated the weights based on this algorithm, you go back to point 2. So you take another point, you do the same operation, and then you do update the weights again, and so on and so forth. For example, you can implement this algorithm in a code with a simple for loop. And this is the example that we have in the notebook that is in GitHub. And here, in this case, besides doing this, at every iteration, we also print the result so that you can see in real time how the weights are being updated. And this trains for a number of iterations is not very large, like for 100, and with a learning rate of 0.1. And you already see that after this, you already get to something that reproduce your data quite well. What happened now? By progressively updating the weights, the neuron has found out that a specific value of the weights is able to reduce the difference between each prediction and the ground truth. So in this way, it's approximating the function that was defined to generate those data quite well. It's missing one point. Do you know why? Can you tell why? Mm-hmm. Not exactly. So let's look at the data, no, the black points. So you see that you get a value of 1 in the y when x is slightly negative. Huh? Yes, it's along that line, but basically, so the issue here is that the network will never learn this kind of behavior because we are not giving to the neuron enough freedom to learn this. If you remember the function that we wrote, where is the function? Is this one wrong? So basically we have one weight, one number that multiplies one other number, which is the input, and then just sees if that number is positive or negative. But there's no offset. So this can predict a heaviside function, a step function, but it's not able to shift this function. And what do you need in order to shift the function? Something that we didn't mention explicitly, but that is here. See, we have all the inputs. Each input is multiplied by its weight, but we can also have a bias. A bias is another parameter of the neuron that does not depend on the input, but it's just shifting the function. So if you have a function that has a change point at some negative value, you tune the bias in order to accommodate that behavior. Same thing if it's very positive. But the way we wrote the neuron so far, which does not have a bias, will never be able to reproduce the behavior that we see in the data. So in that case, we don't have enough parameters to reproduce that. But that is something easy to do because basically you just have a fake input of 1. If you add to your network, to your function, that they can also handle a fake input of 1, a dummy input, then you have another weight, which in this case is called bias, that is able to do that. Okay, let's go back. Okay, good. Just a general, we will see later. Let me see. So you also have exercises based on this, and with you can play with different data set in order to see how the network behaves. And but let's now move to something else. So far, the problem that we have been dealing with was extremely simple, was trivial. You have a one-dimensional input, so you have one number at the time, and for that number, the neuron predicts the output, 0, 1. But you can have data that are, typically you have data that are quite more complex than that. For example, we can start increasing the complexity by moving from 1D to 2D. And for that, we will use, we have to modify the function that we created before for plotting and so on. But basically, we will write, we will have a prepared data set that now it's an NumPy array that contains couples of numbers, which represent the inputs of the neuron. So now it's like the input is, if we think about the biological example, it's like the neuron has two synapses that are signaling in, and based on these two inputs, is gonna fire or not. So each signal provided by the synapses, its number. So you receive a couple of number, a pair of number at the simultaneously, and based on this, you do the calculation, you do the prediction. I mean, we can represent it. We can write a function to represent it. And in this case, now we have 3 dimensions, no? Because we have the 2 input values, the 2x, and the y, which is the prediction. One way to represent it is basically use the xy plane to put the input as x0, x1, and then put the y, the prediction or the ground truth in a polar code. And in this case, we have yellow if that is 1, and blue, it's dark blue if it's 0. So what do we have in this case? Can you see which function we are representing by just looking at this plot? So this is a separation between 2 planes, with the plane in 2 parts. Now, basically, you have it seems like you have some sort of straight line that divides one part of the plane from the other. In one part of the plane, you get values that are around 1, and then the other part you get values that are 0. So if you think about it, this is like having a step, not a step function, but a step surface, no? That starts 0 in this direction and then crosses to 1 going in this direction. And we should be able to reproduce this behavior using the same neuron as before. The only thing that we need to change is that now the output does not depend on 1 input, but on 2. And for that, we can do some modifications. Sorry about this. I forgot that this trackpad is very... Okay. We're here, okay. So something that, some general information that is useful if you go through the book or through the code. Every once in a while, you see that we have the code with some characters or some part of the code in bold. That means that we are reusing previous code with some modification. So basically here, we are using the same function that we defined for the neuron classification in 1D, but now we change the name, so we call it neuron classification 2D because now we have input in 2 dimensions. We change a bit the instructions. I mean, for this function, say now this work for the multidimensional case. And then this is the other part that we change, because now what we need to do is not an operation between 2 numbers like we did before, but it's not a simple multiplication between the input x and the weight w, but now we need to do a dot product. So we need to multiply each input by each weight and then sum up the result. And this can be done using this symbol, no? This at symbol. But then besides this, we have exactly the same as before. The only thing that we do is that now this calculation is slightly more complex, but no big deal. Still, we are calculating something linear, a linear function, because it's a linear combination of input with weights. And then the nonlinearity is introduced when we do basically the logic operation to see if this is larger or larger than 0 or not. We can again normalize, initialize everything with random weights. We can calculate the output. We can plot it by modifying the function that we had before. And this is our result for a random case. And again, we see that in this case, what the network is producing, it's something that does not have much sense. Because now it's generating these step surface with some orientation that is saying that whatever is on this side of the x-axis is 0, and whatever is on this side, it's 1, because you see that the crosses that now represent the prediction of our neuron are blue on this part and yellow on this part. So basically, the data that we have seems to represent a surface that steps from 0 to 1 at some point, going in a direction that seems to be like 45 degrees with a negative x-axis, whereas the prediction based on the random weight switches when we go from the negative to the positive part of the x-axis. So we have a surface that steps when we move along the x-axis of this plot. Again, this is the result, as we saw before, of the fact that you're using a random number. And we need to teach the neuron what is the real weight that approximates the function described by our data. And we do that in exactly the same way as we did before. There are a few changes that we need to do. One is that now we have not a single value, but we have a vector or an ampere array. We need to use the function that we defined for the two-dimensional case, not for the one-dimensional case. But besides that, everything is pretty much the same. I mean, we also have to change, update the name of the variables when we calculate the updated weights in the function. We need to print the right quantity in this case. But if we do that, then we do run it for a sufficient number of iterations. In this case, if I remember correctly, is 100. We get that in this case, the neuron is able to perfectly predict the output that we already knew of the data. What is the point now? I mean, the point is that if we have extra data that are of the same nature of the data that we use for the training, we can use this neuron to make a prediction for something we do not know the prediction, the output. Of the data that we use for training, we knew everything, also because we prepared them. We know that given the value of x, what is the value that you have to expect, 0 or 1, to which class it belongs, positive or negative. But now, let's suppose that we have another data set that is supposedly of the same nature. We can use our neuron to get a prediction for this data. Okay, one thing that we can easily do to solve the problem that I mentioned before when we saw that the function, the neuron was not able to predict correctly all the points in of the data because he didn't have the possibility to shift the Heaviside function, to shift the step function, is to add a bias. And one way to do it is basically to add it as another dimension in the function. So basically, we need another parameter b that we need to update, similar as we do for the weights. Let's see how that is included in the code. You see that we need to add the line that now updates this bias at every iteration, at each iteration. What is the difference between the way we update the bias and the way we update the weights? You remember the function that we had before? So we still use the learning rate, the same for everything. The error, which is the difference between prediction and ground truth. But when we update the weights, eta multiplies the error that multiplies the value of the weight at that point. The value of the input at that point, sorry, the weight of the input. In this case, we're considering like the input is equal to 1. So this is like having a number of input that besides the real input as a unit. But then besides, I mean, if we adapt this line, everything is pretty much the same. Of course, we can also print at every iteration the value of the bias, and then we can train the network. And one exercise that is nice to do is to see that if we now include this, and we run again the learning on the previous data, now we are able to capture the fact that some negative value correspond to a high to a one output in the original data set. There is something that it's very general and very useful, which is that the value that basically the weight are initialized randomly. And when we initialize them, we can control their value, because we can, for example, can generate a random number between 0 and 1 or -1 and 1. But basically, it's always a good practice when you deal with the neural network and deep learning in general to have values that are not too large or not too small. So we need, during the training, we need to make sure that these values do not diverge or do not go to 0. Because otherwise, I mean, for example, if you start having weights that are too large, the network can go crazy. Or if you get weights that are 0, you're not updating anything. One way to make sure that this does not happen, there are many different ways, and then depending on the specific architecture, you can implement a combination of these. But one thing that is very useful is to use some regularization. What does it mean, regularization? Basically, you impose the weights or the combination of the weights to be limited somehow. One common way to do that, for example, is to do weight regularization in the way that you see here. No? Basically, you divide each weight by the norm of the weight vector. Let's go back again. What does it mean, this? Basically, you're making sure that in all the possible cases, think of the weight vector as a vector in space, no? And basically, by changing the value of each component, you're changing its orientation and you're changing its norm. But we can make sure that the norm at each step is unitary. So basically, you move your vector on a sphere. And in this way, you help the algorithm to find the solution in a more efficient way. And this is something that is very easy to implement in the code. There is something that is very important that is strictly related to the neuron that we have described since the beginning. So in the implementation of the neuron, we introduce nonlinearity with a simple logic operation. Basically, you compare the activation potential with 0. And at that point, you're doing the nonlinear operation because you're transforming the input in 0 or 1. Basically, that corresponds to use what is called an activation function that is typically indicated with sigma. That is a heaviside step function. So you take the value of the activation potential. If it's smaller or larger than 1, you get 0 or 1. But there is one problem with this function. The thing is that if we are in 0, how is the derivative of this function? Hello? Am I losing you? Is anyone awake? Sorry for waking you up. How is the derivative? No, but I mean, I'm just talking about the heaviside step function, no? In 0. It's discontinuous. So if you want something that has, which you can define the derivative almost everywhere, you need to find something that is continuous. So typical functions that are used to introduce this nonlinearity are those that you see here, no? And for example, for classification, typically I use the sigmoid or the parabolic tangent, depending on the range of your input data, because the range of your output data, because in one case you get values between 0 and 1, in the other case you get values between -1 and 1. So depend on a bit on the normalization that you have on your output data. But for I mean, so far we've been talking about classification. So you want an output that is digital, let's say, that corresponds to classes. But there are other applications that we will see later on in which you want the neuron to predict not an integer value, not a class, but like a continuous value. In those cases, it might be useful to have different functions that are not limited, they do not have their output limited to a discrete number of values, but can give you a continuous range. The easiest way to do that is just introducing a linear activation function. We basically just you take the value that you get out and you use it to compare your data with. Or in some cases, you can use a ReLU that is a rectified linear unit. What does it mean? That you take the output only if that is larger than 0. In that case, use a linear function for activation, but if it's smaller than 0, you do not take it. Why this is important? Because, I mean, if you use a normal linear function, you are not introducing nonlinearity. You're still using a linear function. So the network is still somehow limited in what it can learn. The ReLU, it's a good trade-off between having some nonlinearity, so basically throwing away some of the values that you get out because they correspond to no output, to 0. But if they are above a threshold, you use them as they are in a linear way. And then there are other combination of this mechanism in which you have a leaky ReLU that you take the negative part, but with a modified slope of the output, and then you use the linear function only for the positive one, etc., etc. But basically, what is important to have is that something that is differentiable in order to generalize this process, as we will see right away. Okay, so far we have been limiting ourselves to very simple problems. We have set of data. Each data corresponds to 1 or 2 inputs, and we want to produce an output, which is one number. Of course, this helps to solve some problems, but this is, I mean, what we're been trying to approximate is like a logistic regression. It's nothing more than logistic regression trained in a different way. So we're not optimizing the value of the logistic regression with some maximum likelihood estimation, but we're doing in a way that is based on the data that we have and the algorithm that we described. But the real power of these methods is when we have problems that are more complex. And in this case, the thing is that the neuron has a modularity, can be used together with other neurons, and you can have basically a layer of neurons that do simultaneously operation on the same input and produce different outputs. Not only that, these outputs can be combined, for example, using other neurons. So basically, we can imagine to pile up together neurons that produce operations or with respect to the same input, and then stack layers of neurons together to complicate even further these operations. And there's no limitation to the number of neurons that you can use. And this brings us to the definition of a neural network, because now if we combine neurons together, we can produce outputs that are not as easy as a step function with a shift in a plane or on an axis. But we can, for example, in the case in which the output is bidimensional, describe any partition of the plane that we want, either convex or not. For example, what do we have here? This is a schematic example in which we have an input made of 2 values, so basically a vector of 2 elements that are transformed by a first layer, a first set of neurons in which the weights have been chosen to produce a specific output. So basically, what do we have? We have the first neuron here that takes a bias of 0 and then combines these 2 input values, each with a weight of 1. So basically, it's taking the sum of the 2 inputs. And since the bias is 1, is 0, the output of this is just the sum of these 2 inputs. This other neuron, what is this doing? It's doing the difference between the two inputs, because now it's multiplying the first element by 1, the second by -1, bias 0. And this is producing an output based on the difference of these two. We have a third neuron that now is doing something even more basic. It's only taking the first input, x0. It's not taking the second one because the weight is 0. It's shifting it with a bias of -1, and it's producing the output. So basically, the operation this is doing is x0 minus 1. Each of these three neurons is producing an output. So basically, it's producing three numbers that can be either 0 or 1. And these three numbers are combined together with another layer of neurons. In this case, we have two neurons in which the weights have been chosen in a different way. Here you can see that this is basically multiplying each of the output of the first layer by 1.5 and then adding a bias of -1. Here something similar, but you multiply each input by 1.2 and then use a bias -3. What do you produce? So basically, each neuron produces a different partition of the space. And then each layer combines this partition together. So you end up basically by describing something that is represented by this bidimensional function. So you still have this sort of step function, but the way in which they pass, the position at which they pass from 0 to 1 is rather complex in space. And basically here you describe these two quadrants plus half of these two, and here you just describe this section, this slice of the plane in this way. The important thing is that, so here we are dealing for the first time with a network of neurons, a neural network that has input, an output layer, and this layer is typically called the hidden layer. Why hidden? Because you don't see the output directly. And a network of this kind can approximate, in principle, any function. There's a theorem that shows that given particular conditions, with a network as easy as this, you can approximate whatever function you can think of. General approximation theorem. The thing is that you can go even farther. So because this is what is typically called a shallow network, because you have just one hidden layer. But the number of hidden layers can increase. And the higher the number of hidden layers, the deeper the network. And if the network is deep enough, we start talking about deep learning. The definition of deep learning comes from here, but from the number of hidden layers that you have in the network that can offer more solutions to your problems. They can generalize better the unspecific output given the input. Now, when you have a network like this, the algorithm for the optimization cannot be as simple as the one that we showed before. We need to include more ingredients. What are these ingredients? Let's go through them. We can see, for example, that in action. Yes. No. I don't have the answer by heart, but I will say so. I mean, in principle, you have limitation on the set of, but not on the type of function. I need to think of, I mean, I will say yes, but the differentiability, I mean, is not, so the function in this case, I mean, I don't see, what I don't see here is the link between the differentiability of the function that we are approximating and the requirement of differentiability of the network. So there are two different things. You can approximate a function that is not differentiable, but using a network in which you have functions that are differentiable. I mean, can you generate a data set that predicts that behavior in a specific range? If you data that predict the behavior of the function in a specific range, I guess you can train and run that for that. The thing is that it's limited to the range of data that you have. You cannot extrapolate.
And then I think one important point is that technically the general approximation theorem, what it says is it's possible to approximate any function with a single hidden layer, but that single hidden layer has infinite neurons. It's actually what it shows.
But I mean, practically you can combine different layers at that point to
Yes,
have,
that's how you.
yes, to have a solution that it's to get to a solution in a more efficient way.
Yes.
But I mean, the specific answer to your question, I don't have it right now. I have to think about it also because I don't remember exactly all the peculiarity of the functions that you're talking about. We can talk about it later.
I think maybe it's important to point out because you showed in the last plot that the first.
Stand up. I mean, they're recording. They want to see you.
Yeah, and if you could scroll up a little bit.
Sure.
Because you can see in the first plots there that the first hidden layer actually learned really simple correlations. Yeah, there, the first layers. You just get these sort of linear separations. And then in the second layer, which in this case happens to be the output layer, but it could be the second hidden layer, you get these much more complex correlations. And this is true in general for deep networks. So the deeper you go in the networks, the more complex correlations you can find.
Yeah, that actually brings a very interesting point that I forgot to mention. So if we look at what we have here, no? This very simple separation created by the first layer, we have this partition of the plane. But then this and this, what do they correspond to? If you think about it, those are the implementation of the union at the intersection of the planes defined by the first layer. So the first output is basically the union, no? If you superimpose all the planes that are generated in here, you get that. If you intersect them, you get this. And when playing with this, you can basically get to approximations that are even more complex. Okay. Okay, let's now consider this data set. No? Now we have a two-dimensional data set. Still, same representation as before. You have base data that belongs to three quadrants seems to have an output of 0, a prediction of 0. One quadrant seems to be positive. There is some overlap between these two, so there is some noise. Let's say it's not a sharp separation. And we want again to have something that is able to predict this behavior. So a function, a network that is able to give predictions that corresponds to the ground truth, which is what we see here. So at this point, we need to define one of the more complex activation functions that we saw before, which is the sigmoid, no? For the sake of differentiability that we mentioned. The sigmoid is easily defined, as we see in here, because basically what you have 1 over 1 plus an exponential, a negative exponential. But let's now think about how we want to update the weights. In order to understand how we need to update the weights, we need to understand what are the operations that we do in this simple network. So basically, what do? We have a function that takes the two inputs, and we call and each input has a specific weight, A and B. So the inputs are in the vector X. And then we have the first layer. So the input X, just for, I mean, the code is written not in a way to be efficient. It's written in a way to be very understandable by just reading at it. So basically, we define like X sub A is same vector X. Why? Because A, in this case, it's a label that refers to the first layer. So everything that is labeled A is the first layer. So we have to take the input and do the dot product with the weights that belongs to the neuron of the first layer that we call WA. And this produces the activation potential, so the output that we have within each neuron that we call PA. And on this value, we have to apply the nonlinearity, the sigmoidal function, the activation function. And so since we have defined the sigmoid function, we just take the one y sub A, it's a sigmoid of this. So basically, at this stage, we have the output that the first layer of the function is calculating whatever is the input vector X. But now this output serves as the input of the second layer, which in this case is the final layer, no? the output layer. And we have to repeat the same operations. So again, for the sake of readability, we define the output of the first layer as input of the second one. Multiply them with a dot product by the weights of those neurons, take this sigmoid, and then the output of this layer, since we don't have any further layer, is basically the prediction of our network. So this reproduces the behavior of the network. But in this, there's no update. There's no algorithm to change the value of the weight at each iteration. This is the part that we miss. For doing that, we need to calculate something else. Before that, let's just see how this network works. So we can just define, for example, the number of neurons that we have in the network that we described earlier. We define random weights, and then we do the prediction and we plot it. And here there is a problem in the colors of the image. But basically, if you have one of the new copy or the electronic copy of the book, you will see that so if you remember, these three quadrants had a blue value. This quadrant had a yellow value for the real data, for the training data, and the prediction, since it's random, is producing something that is different from this. I don't remember exactly what that is producing, but something different from that. Because again, we're using a random initialization of the weights. We didn't teach yet the network to what the weights are. But now we need to find a way to train it. And here's when we have to define something that is crucial, which is backpropagation. And for that, we need to include some mathematics. Let's think at the process that we described before when we talk about one neuron. So we were updating the weights based on the difference, roughly speaking, between the prediction and the output. But from the mathematical point of view, what does that correspond to? That corresponds to, first of all, defining an objective function. We want my data to be as close as possible as something else. And this function, for example, can be, the square of the distance, the sum of square of distance between those points, or the absolute distance, so the absolute value. So mean absolute error can be one possibility, or or root mean square error. Then, based on the value of this function, you want to update the weight. So basically, you want to do that using the derivative, as we've said before, no, in the example that I was mentioning before, in which you have basically a parabolic function, or something that you can approximate as a parabola. You want to find the minimum of that. In order to move toward the minimum, you take the value of the gradient at the specific point. So if the gradient is large, it means that you're far away from the minimum and you need to move a lot. If you are close to the minimum, the gradient is small and you have to move less. That we need to multiply the learning rate, but the crucial part is the gradient. The thing is that if we have a network like this, we can calculate the gradient of the final objective function with respect to all the parameters in a chain way. So basically what do we want to do? Let's suppose that this is our objective. Let's start from the end. And we want to calculate how this objective function depends on the output, the prediction of the network. The way to do this is to calculate the value of this output with respect to the weights, or to the potential, to the activation potential of the neuron. But the activation potential of the neuron depends itself on the weights. So basically, you can decompose the derivative in different parts. So you can take the derivative of the function with respect to the output, the derivative of the output with respect to the potential, the derivative of the potential with respect to the weight. And why this is useful? Because, I mean, if we can apply, as we will see later, this process not only to the last neuron, but also to the previous neuron, based on the final result, you can go back and based on all these derivatives, changes the values of the weight at each iteration. This is why it's called backpropagation, because basically you update the value of the weight from the last part, from the calculation of the objective function, or the loss function if you want, but then you go toward the direction opposite to the one in which you propagate the information. So you start from the input to get the output, you compare the output with the expectation, which is the ground truth, and then from that point on, you calculate the derivative, you update the weights in going backward. So the fact that we can use this chain rule makes all the process extremely efficient. Because at that point you don't have calculate anything of every different function. You calculate the derivative for each single step. And this, for example, is something that is implemented in the typical libraries that are used for deep learning. You want to add something to clarify this point, Jesus, Eric? Because this is very important. So if you have a different way to describe this, it might be useful.
No, I think maybe just pointing out, is I think that the one crucial part here is, I mean, if deep networks are so amazing, why don't you just make deep networks with 200 layers? And yet, does anyone know why you don't do that? Just add 1,000 layers and then you get amazing performance. Yeah. Great question. So the general approximation theorem says that one layer is enough if you have infinite neurons in that layer. Well, because it's inefficient, right? Because then you have to go towards infinite neurons, but maybe just by adding a little bit more.
No,
it depends on the function.
There's no rule for that, but you can try. I mean, this is an exercise that we did actually. In one of the classes, because typically we do this course, as I was saying before, in 5 days. So we did that. So you can create, for example, something that's like a non-convex function that generates some input, some output data. So that problem is already, complex enough, and you can start just train a single layer network to approximate that. And let's see, and basically check how many neurons you need to approximate that, and how long does it take to learn. And then you just add another layer. and see how the process becomes more effective. Of course, it's a problem-dependent answer. There's no general answer. If a problem is simple, probably you can solve it with 2 layers. There's no need to, with 2 neurons, there's no need to add any further layer. But I mean, if the same problem can be approached like, with 100 neurons in 1 layer, or 7 by 3 neurons in the 2 different layers, probably the second approach is going to be faster and more efficient. I mean, those are examples made completely made up, but it's a bit of trial and error. And I mean, something that based on experience, it's very important. It's your knowledge of the problem. If you know very well the inner working, let's say, of your problem, you can design a network that's more efficient for it. But as far as I know, there's no general rule for how to design a network given a specific problem.
And it also depends on the problem, right? Like, I mean, for example, if you work with images, you don't work with a dense neural network, right? A dense neural network can be a very small part of a bigger network, right? So you start stacking multiple neural networks to map complex functions. So locally speaking, what a dense neural network in most of the cases need to solve is a very complex, very concrete transformation, right? In this complex mapping space. So in practice, it depends on the specific application. Sometimes dense neural networks can be just linear transformations within a very big neural network. You know what?
I didn't say that it's not possible. Maybe you can. I don't think anyone ever did that.
I mean, there are these automatic hyperparameter sweeps and so on, packages that do basically exactly this. They try to, I mean, but given a very fixed data set and a fixed architecture, you just try to find the optimal number of neurons, optimal learning rate, optimal so on and so forth. So you can do it in, I mean, very
But
constrained
it's empirical.
Yes, yes.
So
Yeah.
I
Right.
guess it's referring
Purely
to some
theoretical.
theoretical.
Purely theoretically, I've never seen it.
Never
seen it. Yeah.
It might be that there is some theorem that gives some hint in that directions, but I don't know. I'm not aware of that. That it's. I mean, typically the mathematical formulation of these things are quite involved. And
I know. I mean, one rule of thumb you can at least start with is that usually the number of neurons should be in the same order of magnitude as the dimensionality of your input. That's one simple rule of thumb. If you have a dimensionality of your input of a vector of 4,000, you don't want to have 2 neurons, right? You want to have something in the order of 1,000. These types of things. But there's no direct theoretical reason for that, I don't think. It's mostly intuition. But yeah, I mean, the point I want to make here is just the reason you don't stack deep networks really, really deep is because you have this this component here, which is the derivative of the activation function that's multiplied in each step during the backpropagation. And if you remember the activation functions, they were all between 0 and 1. So if we take the derivative, they're all between 0 and 1. So every time you multiply by this component, you multiply by something that is between 0 and 1. Meaning that for every layer in your network, you're actually multiplying the loss, the gradient change of your weights by some number between 0 and 1. That's called vanishing gradients. And you can test that. You can try training a 2-layer network and then a 100-layer network. And the 100-layer network will just not train. But there are ways to get around that too, which we get into in later chapters.
And the other thing, I mean, from here you see the need of differentiability of the activation function, no?
Yeah.
Because basically the derivative of the activation function where is here. It's the derivative of y20 by p20. Because basically here you get the activation potential. So the neuron is combining the inputs multiplying them by the weight and summing them up. But then, in this case, F is the activation function that is making this nonlinear. So the derivative of the y20 with respect to p20 is the derivative of the activation function. If that explodes, I mean, you cannot update anything because then you get infinite values and okay. So from the mathematical formulation, basically we can calculate exactly the values of the derivative that we need. And in this case, we need them because those are important to write the update rule for the weights. I mean, I will not go through the mathematics of this, but basically, I mean, it's described here. And then if we trust the calculation and we did they're made that we were fine, we can just jump to the implementation into the code. So you see that now we have what we already had before, which is the part that we use just for the calculation of the output of the first layer and the output of the second layer. And then we need the weights updating part. And here we see that, I mean, it's not overly complicated because basically we have, I mean, in this case, what we used as an objective function, it was written in here. Where is it? Just to show it. We use the mean square error. So basically you take the distance between the prediction and the objective function. So when you derivate this, you get a linear function, which is nothing but the error, what we call error before, the difference between the prediction and the ground truth. So we keep that into the implementation of the weights updating part, because you have the error. That is nothing but the difference between these two. We multiply it by the derivative of the activation function, the sigmoid, and then when we update the weights of the first layer, we use, you know, the value of the inputs plus this delta, that is the product of the error, so the derivative of the very last part that we saw in the scheme, plus the derivative of the activation function. And then, of course, this is what applies to the final layer, no? But since we're going backward, then we have to do the same also for the weights of the first layer. But the operations are quite similar because, I mean, the chain rule is very easy. Of course, we have to introduce in the calculation of the first layer some information that was coming for the second layer. Because, I mean, obviously, because this is a consequence of the fact that the input of the second layer is the output of the first. And then you have to propagate that also into the derivatives. But basically, with this change, I mean, you can now train, similar as we did before, something that is way more complicated than a single neuron, because, I mean, it's creating this combination of neuron that can produce very general and complex results. The important thing here is that, I mean, so here we are kind of generalizing it to the case of one hidden layer, one output layer, 3 neurons, 2 neurons. But this, I mean, it's very modular. I mean, although, I mean, I repeat, this is not the most efficient way to implement it in code. It is already quite straightforward to extend it. There's basically just to have to copy paste pieces of this and then vary the number of parameters. With this basic function that we have in here, you can already vary the number of neuron of the hidden layer and number of output neuron. So you can already have more complex situations just by changing some numbers. So not changing the function. The function is the same, you just change the numbers. And if you want to add further layers, you just have to copy paste blocks like we did here. Okay, so again, you can train this, you get the prediction. This is one of the other images that appear black in this version of in this electronic version of the book. If you have the new one that has been corrected, but basically in this case, we see that we are able to reproduce the results quite well, almost perfectly. So what time is it? We still have. Let me see. We have half an hour. Let's see what we can do. Probably the best idea is to see an example. So as I was saying before, this network can be generalized to a higher number of layers, but in real life, probably will never have to write this network by yourself, besides for the purpose of learning how it works. What typically one can do is to use some library that already has pre-built networks. And a network of this kind that can be, for example, obtained using a library that we developed that is called display, and we will see in a second. But we will see that to solve a specific problem, that it's a very general problem, probably one of the examples that you will find in every web or a book that speaks about deep learning, and is the classification of digits, of handwritten digits, the famous MNIST dataset. Basically, you have a dataset that corresponds to numbers like this that has been handwritten. This was collected for the IRS in the United States, the Internal Revenue Service, because basically these people were compiling this tax return, and they want to automatically get the numbers from these forms that people were compiling by hand. And the Jan LeCun, that probably is names that rings a bell, developed a first algorithm with the data. We collected the data set and developed one of the first algorithm to automatically recognize this digit. So this is a classification problem, as the one that we saw before. You have an input. In this case, the input, it's an image. Each image is made by numbers because you have pixels that corresponds to a different value, typically between 0 and 255. And out of these inputs that are as many as the size of the number of pixels in the image, you want to decide to which class the image belongs to. In this case, you don't have two classes, 0, 1. You have 0, 1, 2, 3, 4, 5, 6, 7, 9. You have 10 classes. But the principle of the problem is exactly the same. You given a vector of inputs, you want to generate an output, and this output it's a class. It's a discrete output. How can we do that using the tools that we have so far? Again, this is something that I remember if Eric or Jesus mentioned before. If you deal with the images using a neural network like the one that we're using now, is not the most efficient or the most productive way to approach this kind of problem. There are better ways, then we will see it later on. But it's a first approximation, and just to see how it works. What we do? We will use a number of neurons, and the input for each of these neurons of the first layer are all the pixels, or the values of all the pixels of the image. So in this case, we're using what is called a dense neural network, because each neuron receives information from all the inputs. Why this kind of approach is not the most efficient for images? You're treating all the inputs, all the pixels that compose the image in the same way. Of course, each of them will have a different weight, but I mean, in principle, there's no correlation between them. So a network like this is not considering the fact that, for example, if you write a 1, all the pixels that are high or low, depending on how you encode the image, are along a line or something close to a line. If you have an 8, I mean, there's a different kind of spatial correlation between the pixel value in that image. If you just take the value of the input and you put them together in a neuron, giving a weight to each of them, you are losing this correlation, this spatial correlation. You're just combining numbers and expecting that similar numbers combined with weights, that the weights are those that the network will learn, will produce an output that makes sense. As we will see, this works to some extent, but it's not the best way to do that. So how do we do that? I mean, we have the data set. Sorry. Let's go back to the data set. Okay, so here we go. So we have this data set. As I was saying before, we will use a library that already builds this network, and we only need to introduce the parameters of the network they want to build. The library is called dplay, and we import it. And we also import the sigmoid function, the activation function that we want to use, because at the end, what do we want? We want to create something that corresponds to a class. The definition of the network is here. So basically, as you see, instead of having all this function that with all the loops and all the updates, the library is taking part of the hard work. We just need to tell it that we want to introduce as input images. These images in this specific dataset, in the MNIST dataset, are made by 20 by 28 pixels. So the number of inputs that, since we want a vector of input that corresponds to the value of each pixels, we have 28 by 28 inputs. We want to use 2 layers. Each layer will have 32 neurons. So we have number of hidden features, 32 by 32. And then we want that this produces an output that corresponds to 10 classes that are the 0, 1, 2, 3, 4, all the digits that we have as in terms of image. What else do we want? We want that the activation is configured as sigmoid. This is because it was one of the possible choices. It's one that we have been describing so far, and we're going to use that. And then we basically create an instantiation of the model. Again, this is just a convenient way to write, to access code similar to the one that we wrote before, but more efficient, based on PyTorch, that already has this more complex architecture pre-built, and this architecture can be modified in terms of number of layers of parameters by changing this input. All what we have in here basically are some of the hyperparameters of the network, no? Because here we have number of layers, there are 2, and number of neurons per layer. And we can play by changing those and see how the output changes. But basically, if we print this network, we see the detail of what is inside, no? And basically, we see the 3 layers, the 2 hidden layers, and the output layer, no? So you see that, the input, 28 by 28, 784, all this vector with all the pixels, we know we are not considering any correlation between them, are transformed. So basically, each value goes as an input for a neuron. We have 33 different neurons. So we have 33 outputs that combines in a different way the 784 input vectors. Of course, in this case, we consider a bias because we need many parameters to describe it, and bias is an important one. And then, these 32 output of the first layer are further modified by other 32 neurons. And again, each input is combined with all the others to produce some output. And finally, we take these 32 values that come out from the second layer, and we combine them using other neurons to get 10 outputs. And then, depending on the value of this output, we decide if one specific image is more likely to belong to one class or another. And of course, if it's at 0, we expect it to have a very high value in the output that corresponds to class 0. If it's a 9, to class 9, and so on and so forth. The other thing that we need to define, which we did very simply in the first example, it's the optimization algorithm, no? Because the way in which the weights are going to be optimized and the values change during the training can depend. There are many options for that. Here we will use the stochastic gradient descent, which is one of these one of possible approaches. There are many. We will see others. We don't have time to describe the details of them, also because those are very involved. But just for you to know. And in this case, we will use a learning rate of 0.1. What else do we need to define? The objective function. Here, just to keep everything very simple, we use the mean square error loss, meaning that from the output we have numbers that are corresponds to each class. We have 10 different numbers, and we compare these numbers with the vector of the ground truth, which is, if, for example, a vector of 10 elements in which one corresponds to the class where the number belongs to. For example, if we have an input which is at 0, that has been labeled as a 0, in the output vector in the ground truth, we will have the first element which is equal to 1, corresponding to class 0 equal to 1, and all the others equal to 0. So we have the vector with the 10 prediction. With the vector with the 10 ground truth, we take the mean square error loss. This is a choice, probably not the best one for this kind of problem, and we calculate that. And we want to minimize that. And this stochastic gradient descent is the algorithm that we want to be used to basically optimize, to minimize this loss over and over for each iteration. Again, we define the number of classes of the output. The model is the one that we instantiated before. We now instantiate also this classifier. And then at this point, I guess we are ready to run the code for training. Again, we can see the output of classifiers that gives you this information. And in order to start the training, you need to find a way to pass the data to this model that we have created, because so far we've been creating the architecture. We have been changing the hyperparameters, but we didn't tell the network which data it should get. For that, we need what is called a data loader. The data loader basically is a utility function that collects the data that are saved in some variable. In this case, we load the data and put them in this training images digits structure. And then the other information that we are telling here is that when these data are going to be passed to the network, they can be shuffled. I mean, they don't have to be always in the same order. Why? Can you think about the reason for that? What is the network doing when it receives the data? It's the same. I mean, it doesn't really matter. I mean, it might be that these images are ordered somehow, no? Because those are being collected. So it might be that you are presenting those images in a specific order. So you need to randomize, as we did before, the calculation of which data is going to be used at every iteration of the network, in order to make sure that you don't receive images that belong all to the same clusters together, because you're creating a temporary imbalance. The network needs to optimize a general solution, all the classes together. If for a while it sees images only on one kind, can be biased toward one solution. This is one of the reasons. It's not the only one. We will, in order to explain the other one, we did some of the concepts that we haven't introduced yet. But basically, so at this point, we define what is called a trainer, which is basically the structure that runs the process. And here, we're using another concept, which is the concept of epochs. When we talk about the simple neuron or the simple network, we were passing the data for the calculation of the gradient one by one. And at each new data set, we were calculating the gradients and updating everything and so on. A better way to do that process is, for example, to pass all the data together. Because at that point, the network does only one optimization because it's receiving all the data at once, and it's seeing all the variety of the data, and is able to do the calculation in, for example, in one step. No, it does can optimize fast. The thing is that typically you need a lot of data to do the optimization. And if you need a lot of data, calculating something on huge amount of data can be very slow. So a trade-off between one data point at a time and all the data together can be to use mini batches. So basically, you create a random selection of your data set, but composed by a smaller number of data points. You pass it to the network. Network calculates gradients, does backpropagation, updates the weight, and then it receives another batch of data and repeats this over and over. At some point, the network will see all the data in the dataset. That is called an epoch. So basically, it completes the process of optimization, seeing all the data points in small batches, and then it's ready to repeat that operation again. When the operation is repeated, it does the same, and then you can decide if the data are shuffled differently, so if the batches are randomized in a different way, or they're kept in the same. I mean, there are options for one or for the other cases, depending on specific situation. Basically, here, by saying max epochs equals to 1, what are we saying? That basically the network will see all the dataset once. Not even, no more than that. And then, based on that, we can train and see the results. I mean, all the examples that we have here in the book and on the GitHub are being tuned in order to run in a decent time on a regular computer. If you want to run them even faster, what you can do is to run them on Kaggle or on Colab. Are you familiar with Kaggle or Colab? You know what they are? Okay. Because I mean, in that case, you can also use the GPU. You can just have some free time from free GPU times, so this will run even faster. But I mean, even on a CPU on a regular computer, most of the examples, in particular those of the first chapters, will run in a time of the order of minutes. Okay. So this is some utility function to plot the data, and we can see that after training this data set, we can see the results in a confusion matrix. What is a confusion matrix? A confusion matrix is a matrix in which you have a number of rows and columns corresponding to the number of classes that you have in your problem. And basically, having a high value on one of the elements of the matrix, it corresponds to how many prediction you have for the corresponding specific value of the ground truth, or vice versa. But for example, in this case, what do we have? That, for the ground truth digit equal to 0, so first row, we get the most of the predictions correctly assign them to 0. Because you see that, probably we have like 1,000 ground truth equal to 0. So 1,000 values of these input images are being assigned manually to the class 0 by some expert, but some human annotator. And 963 of them are correctly classified by the net. That is quite good for one same. But it's not the same for all the numbers. For example, you see that, for number 4, it's also quite good. But for number 5, you see the number of number 5s annotated by somebody that the machine found it's quite low. It's 4. Most of the number 5s are assigned either as 0 or as 3 or as 7. Why? First of all, because I mean the network they were using is very simple. Second, because I mean probably we haven't trained it sufficiently. Third, I mean a 3 and a 5 can be confused depending on who writes it. So we need some further information that we're not introducing, that we're not letting this network learn to improve that. What are the hardest number to classify? 8 and 9 are also quite hard. You see that 8, you see a decent number of 8 correctly predicted, but there are a lot of confusion with 2 and 3. I mean, 8 and 3 can be easily confused. I mean, in particular, if you don't have enough resolution in the image. 9 is the same. You have 100, but you have a lot of 9 that are confused by for 7 over 4. So again, not an easy task. What can we do? We can do several things. One thing that we can do, I mean, so far, as I was saying, we were using something very basic. Something that we can do is what is called a softmax activation. What is softmax activation? Remember that the output of our network is predicting 10 different outputs, no? And we're comparing these numbers with a vector that is either 0 or 1, depending on of how the data set has been annotated. We can modify the output by using this function. No? So if y sub m is the output of the network, we can basically normalize the output numbers using this, so dividing by the sum of the exponential of this number. And what do we do? What do we do in this case? What is the? Well, I mean, of course we do this because we expect an improvement. But why do we expect an improvement for this kind of operation? We are making the output most similar to a probability distribution in this way. So basically, we are introducing something that sums up to 1, for example, and we are giving it more relevance to the higher number between this 10. And if we just do that, and I mean, here we show with using the code that we can simply change this activation, because I mean, we're changing only the activation of the last layer, no? Just before the output. And we're configuring it in a way that is not a sigmoid, all the others are still sigmoid, but this last one is a softmax. So basically, we pass it through this normalization based on this sum of exponentials. And then if we do that, we already get something that looks much better. Because now we see, I mean, we are closer to the optimal result. What is the optimal result of this network? I mean, we expect that a perfectly working network will have all the elements on the diagonal, on the main diagonal, because it means that the network is predicting correctly exactly what it was annotated, was labeled correctly. So we will expect to have all the elements on the diagonal equal to 1 and all the others equal to 0. I mean, it improved, but it's still not perfect. For example, you see that for number 8, we still have some issue, and for the number 5, 2, and for the number 9, 1. I mean, it improves a lot, in particular for the number 9, but still it's far from being perfect. What else can we do? Very quickly. I mean, so far we're in a situation in which we have all the activations within the inner, the hidden layers that are the same as before. We just changed the last one. And we're using sigmoids for the hidden layers. But I mentioned before that sometimes it's more practical to use a different kind of activation, which is the ReLU, the rectified linear unit. Why? The rectified linear unit basically excludes the values of some weights, because basically it gives output 0 if the output is equal to if the output is lower than the given threshold. If basically if you have the potential that you calculate on the node, if that is lower than 0, you get that node is off for a specific value. So by doing this, you can improve further the results. I mean, you can see that the change of activation at the level of the code is done here. It's just that the first part in which you have the activation of the, in this case, is equal to ReLU. And basically you are changing now the activation of all the layers except the last one, because the last one is what we already modified before. So we have the 2 points minus 1, meaning we change all the layers of the network, activation of all the neurons of the network minus those of the output layer. And if we do that, now we see that it gets even better. And you have this activity, this metric that is nearly diagonal, is not still, it's not perfect, but it's quite closer. And the result in terms of accuracy of this network, I don't remember the value, but it's something around 94%. So this is comparable, if I remember correctly, to the value that Jan LeCun got when he published the first neural network on the first convolutional neural network on this data. Of course, we will see that using a convolutional neural network, and we will define later what that means, improves a lot these results, because with a convolutional neural network now you're able to exploit correlation between different pixels. Basically, nowadays, a problem of this kind will never be approached with a dense neural network in which there's no relation between the different pixels. I mean, you will start at least with a convolutional neural network. But it was just to show that, even with suboptimal approach, with suboptimal solution, a dense neural network is able to find a relatively decent solution for